Good morning. How you doing, guys? Get on in here. All right. So, good morning. Ready for physics? Let's talk. We got an exam that you guys just took on Monday. So I gotta tell you that it's gonna be a while before I get those graded. It's advisement period is starting now, and it's just there's just a lot on my plate. But I'm working on it, and I'll get them out to you as soon as possible. I may post your answers to your multiple choice questions at some point before I get finished grading your quantitative problems. So that's coming. I'm working on it. Good morning, guys. Hi, William, Tyler, Kaylee. So we're going to start talking about some new material today. And we finished up our unit on work and energy. And part of that material involved this concept of energy being conserved, mechanical energy being conserved in certain situations. The sum total of kinetic and potential. In the absence of non-conservative forces, kinetic energy is conserved. So we are going to look at a new physical quantity that is called momentum. And what we'll see is that momentum allows us to study interactions, and we'll spend most of our time looking at collisions between objects, but the physics we'll learn applies to other situations as well, including explosions, where you have something that starts out as one piece and breaks apart into multiple pieces. So we're going to start this unit by looking at some simulations of collisions, and just looking at the dynamics of what happens when you have two masses that collide. And we'll start with two spherical objects that are moving in one dimension. So we'll restrict our initial considerations to one dimension. But what we learn can be extended into 2 or 3 dimensions as well. All right, and what we'll find then eventually is that if you have a situation where external forces can be ignored, and all that matters is the interaction between two objects, this new physical quantity called momentum is another thing that's conserved, just like mechanical energy is conserved in situations where there's no non-conservative forces. And that's a powerful tool because it allows us to study these interactions in more detail and to figure out what happens as a result of a collision. Along the way, we will define a related concept called called impulse, and we'll see how impulse is related to momentum and how it's related to forces as well. Because obviously, if you have a collision, there's an interaction, there's a force between objects. Okay. So let's start with. Can you get this to work? There we go. We'll start with this simulation. Okay. This is a simulation that's on fet.colorado.edu, and it's something you can play with. There's a Flash version, but then there's, Flash is like being phased out. Even Chrome says Flash will no longer be supported after this year. So everything is migrating to HTML5. Thankfully, there's a prototype of an HTML5 version of this simulation. So here's the situation. you can, you have these two masses, and you can change their, these two spheres, you can change their masses with these sliders down here. Make one more massive than the other, make them equal in mass. And you can also change their velocity vectors by clicking and dragging like this. So let's start out with a situation where, let's make mass 2 approximately at rest. Okay. And we'll make both masses the same size. Uh, 2 kilograms. Okay. And let's watch what happens here. So you'll notice over here there's a slider for something called elasticity. You can make the simulation completely inelastic or completely elastic, and anything in between. Excuse me. And so let's start with the elastic case, completely elastic. What does this mean? So let me reset that. You notice what happens here? So this is a special case where both masses are the same. You have one object coming in with an initial velocity, and then after the collision, they basically exchange velocities. The one that was moving comes to rest, and the one that was at rest starts moving. Does this remind you of any situation that you might have encountered in your lives? Maybe a game that maybe some of you have played. It involves round spherical objects and lots of collisions. Excuse me. Anybody? And oftentimes you have collisions like this. The 5 metal clacking balls. Okay. I know what you're talking about. You're talking about this. I gotcha. So that's the, what's that called? Something's cradle. Newton's cradle. So you can watch videos. I wonder if there's a GIF of this. There we go. So you have collisions going back and forth. So that's true, and all the balls are the same. So what's actually happening with Newton's cradle is it's actually a sequence of many collisions. You have one collision and it propagates through all the balls, and then the energy comes out the other side. Billiards, yes, billiards, that's what I was thinking about. So this should remind you of billiards, because you have, in billiards, all of the balls are approximately the same mass, including the cue ball, and you have collisions like this, where you have this sort of exchange in velocities. So what is momentum? Let's take a look at the momentum vector, and it looks like it points in the same direction as the velocity vector. Okay, so the momentum vector is the blue thing, the velocity vector is the green thing. They point in the same direction. Alright, so we know that. We know that that tells us that momentum is a vector. Uh-oh, we're back to vectors. So unlike energy, momentum is a vector. It's represented by an arrow. Let me change the mass slider. So it must depend on mass, because I changed the mass of the object and its momentum changes. Alright? And it also depends on velocity. Change the velocity and the momentum changes. Okay? So, those are the two parts. So momentum depends on mass and velocity. It's the product of those two things. All right. Back to So let's look at some other situations. Let's reset the situation. I'll turn off the momentum vector. Let's look at a situation where the incoming mass is less massive than the target. We'll call that one that's at rest the target. The red one, the target. Pink one, whatever it is. And the target one, we'll make it 3 times as massive. So watch what happens here. Okay. So what we have, this is very different than the first case. In the first case, you had velocity and thus momentum transferred completely from one object to the other. And here, that's not the case. You have a partial transfer of momentum. So some of the energy of the blue ball is transferred to the pink ball, and the pink ball gains momentum. Okay, and the blue ball bounces and goes back the way it came. Let's change things. Let's make the blue, green, whatever it is, sphere 3 times as massive as the target. So here you have a collision where the pink ball speeds off and it's actually traveling faster than the blue ball was initially, but the blue ball doesn't stop. It keeps going, so it doesn't lose all of its momentum. Okay, oh sorry, I didn't change it back to Chrome. Here we go. So the blue ball comes in and it starts out with momentum and it doesn't come to rest. It's still moving. It still has momentum after the collision. But the pink ball goes from 0 momentum to some quantity and it speeds off the screen. Okay. What if you make it the difference in mass huge between the 2 objects? Reset. So here you have a situation where the blue ball almost bounces perfectly off the red ball and it starts going the other way. The red ball, the pink ball, does gain a little bit of momentum and starts moving, but not very much. So you put all these things together, we're going to look at a case. These are all elastic situations where you have things bouncing off of one another. Now, you may remember, hopefully you remember, that so the reason we call these collisions elastic is because the force that governs these interactions are elastic forces, springy forces. And we just learned that those types of forces are conservative when it comes to energy. So these types of collisions conserve energy as well as momentum. And that'll be an important thing for us to use when we're studying these collisions. Now let's look at a different type of collision. So again, with the simulation, we can look at collisions between completely elastic and completely inelastic. And with these completely elastic cases, what we're seeing is the nature of the interaction. How much momentum the objects have after the collision, after the interaction, is a function of how much mass the 2 objects have. And you get very different behaviors. If they have the same mass in this situation, you get this exchange of momentum. But if the target, the one that's not moving, is much, much more massive, it doesn't gain much momentum at all. On the other hand, if the target is much, much less massive, it gains a lot of momentum. So the nature of the interaction is a function of the masses themselves. All right, so let's look at a different type of collision. Reset this. reset the whole thing. So we're going to now set the elasticity to, or the elasticity to 0%. So that's cool. It makes the black outline brighter on the masses. And let's set it up like we did initially, where both masses have the same mass. And there we go. And let's make mass 2 be at rest. Okay, and mass 1's coming in with some velocity. So watch this. So an inelastic collision is one where so this is not a billiard ball type collision. An inelastic collision is when you have two objects that come together, collide, and stick. They stick together. So this type of collision happens in situations where the force of interaction is not very elastic at all. It's inelastic. Return balls. They stick together. So things that deform, you think of like if these balls are made out of clay, you'd have a collision like this where they stick together. And so they move together as one after the collision. And even though in this picture you're seeing two velocity vectors, one for 1 and 2, they're the same velocity vector because they move as one after the collision. All right, now what happens if, let's look at the values. So I want to set things up here so that, so what we're seeing here, this is the magnitude of the velocity and the magnitude of the momentum, and so the symbol P is used to represent momentum. And M's already used, M is mass. And okay, let's make this mass 2 kilograms. And then you can see very clearly that momentum is the product of velocity and mass. 0.7 times 2 is 1.4. And it has units of kilograms meters per second. So I want to set things up here so that both masses are the same. There we go. Both masses are the same mass. And they both start out with the same amount of momentum, but in opposite directions. Okay, so let me ask you a question. All right, I'm going to ask you, I want you to put your answer in the comments. What is the total momentum of the system at this point? Okay, the system is these two objects, these two balls. All right, you got number 1, number 2, green and red, pink, whatever. What's the total momentum of this system? The way I have it set up right here. Holly says 0. Does anybody agree or disagree? Chris says 2.8. Okay, so this is a little bit confusing because when you look at the when you guys look at the screen, you see these two numbers. The ball 1 has a momentum of 1.4 kilograms meters per second. Ball 2 has a momentum of 1.4 kilograms meters per second. So isn't the total 1.4 plus 1.4 2.8? But you gotta be careful. So what you're seeing, these numbers are the magnitude. See those lines around it? That's the magnitude of the momentum. But momentum is a vector, which means it has a direction component. Okay, and when you add vectors together, and so here it's one-dimensional. So our technique for dealing with vectors in one dimension is make one direction positive and the other direction negative. Okay, so if we call the direction to the right positive, that means the green ball 1, has positive momentum, and ball 2, the pink one, has negative momentum. All right, and So if you have positive 1.4 kilograms meters per second plus negative 1.4 kilograms meters per second, the total momentum of this system is in fact 0. Okay. So, all right. So now it's time to make a prediction. All right. So what I told you earlier, and we can actually derive this fact from Newton's third law, and maybe we'll save that for next time. All right. But what I'm referring to is this property that when you have a collision, and it doesn't matter if the collision is inelastic, completely elastic, or anything in between, the momentum of the system is conserved. The total momentum of the system is conserved. So what does that mean? It means it doesn't change. So if you know what the total momentum of the system is before the collision, that's how much momentum you have after the collision. Okay? Now I have things set up here where we just saw that the total momentum of the system I haven't hit play, but before we run the simulation, the total momentum is 0. Okay? And I also have it set up in a way that the collision is going to be completely inelastic. So the two balls will come together and they'll stick together. So after this happens, what are these two spheres going to be doing after they come together and collide? What are they going to be doing? You know, there's I guess 3 possibilities. They can keep moving in one direction, the other direction, or just come together and stop. Those are the only 3 possibilities. Which one of those is going to happen here? Looking at the comments. Looking at the chat window. They'll stick. That's right, Holly. Holly says they'll stick together. But will they keep moving? They're coming together and they stick together. But after they stick together, are they going to keep moving? Or stop in place? Whatever you want to call it. Okay, I got you. So they'll stick together, but if they stick together, they can still move together as one. But, okay, so here's the beauty of conservation of momentum. Momentum is this vector quantity that you can quantify for an object. It's mass times its velocity. So because it involves the object's velocity, it's a vector quantity. Just like, you know, force is mass times acceleration, and acceleration is a vector, so force is a vector, and they have the same direction. So momentum is also a vector quantity. So you can calculate this quantity for in this case, the 2 objects, and then you add those 2 quantities together as vectors to get the total momentum of the system. And conservation of momentum says that total momentum before the collision is equal to the total momentum after the collision. And here that total is 0. So the only way you can have 2 things stick together and have a total momentum of 0 is if after they collide, they stop. Okay? Before they collide, you can have 0 momentum because they're moving in opposite directions. Boom. They stop. Okay. Do you guys have paper? Do you have paper that you can write out? I'll try to make the numbers easy for you to work with. But let's see if you really get this. All right, we'll stick with the totally inelastic case. And we'll we'll stick with the situation where both masses are equal. Okay? But let's set things up a little differently now. Let's make it so the target over here is at rest. Why can't I get that just at 0? Okay, there, it's at 0. Okay, so both masses are the same, 2 kilograms. Let's make these numbers really easy to work with. Okay. There we go. So mass 1 has an initial momentum of 2 kilograms meters per second because it's moving at 1 meters per second to the right, and its mass is 2 kilograms, so that product gives you 2. All right. The second mass starts out with no momentum. Okay, so here's what I want you to do. Calculate what the total momentum of the system is before they collide here. Okay, you got 2 objects. The green, blue, whatever it is, object, and the pink, 1 and 2. What's the total momentum? You figure out what each object's momentum is and add it together. And then they're going to collide and stick together. So here's what I want you to do. So once you find the total momentum of the system, the product of mass times velocity for each, and add it together, then what I want you to do is try to figure out how fast the objects will be traveling after they collide. So they're going to collide and stick together. And I want you to try to figure out how fast they're moving. Okay? Alright, so here's the setup again. Let's break this into pieces. So and you can put this in the comments in the chat window, alright? What's the total momentum of the system before they collide in this before picture? The total momentum. So you ask yourself, all the numbers you need are on the screen here. What's the momentum of sphere 1? What's the momentum of sphere 2? The total is the sum. The total is the vector sum. Holly's there's got to be other people out there who know the answer besides Holly, but Holly's right. So 2 kilograms meters per second is the total momentum. All right. Now, if we rely on the fact, we haven't derived this yet, but I've stated this. If we rely on the fact that momentum is conserved, which means it doesn't change, the momentum of the system doesn't change before versus after a collision occurs. In the total momentum is 2 kilograms meters per second. Before the collision, what's going to be the total momentum after the collision? Not a trick question. So Holly's right. Let's see if someone other than Holly can answer this. Come on, this isn't a hard question. I'm stating that momentum is conserved. That means it doesn't change. The total momentum before the collision is 2 because sphere 1 has 2 kilograms meters per second, sphere 2 has 0. So after they collide, and in this case it's inelastic, so they're going to stick together, what's the total momentum? 2. Thank you, Katie. 2 kilograms meters per second. Thank you, Davon. So now Can you calculate how fast? So they're gonna collide and stick together, and together they're gonna have a momentum of 2 kilograms meters per second. Can you calculate how fast they'll be traveling? Momentum is the product of mass and velocity. So momentum is going to be 2 kilograms meters per second. So if you know that, you should be able to calculate their velocity. After they collide. What do you think? Katie's got it. So you might be like, well, shouldn't it be 1 meter per second? But essentially what you're going to have here are 2 objects that collide and become one. And so instead of having 2 objects that are individually 2 kilograms, now you have 1 object that's 4 kilograms. So if you take 2 kilograms meters per second of momentum and divide by 4 kilograms, what do you get? 0.5 meters per second. All right, here we go. 0.5 meters per second. All right, let's do something a little bit more challenging. We're going to stick with the inelastic case. Okay, the inelastic case. Let's make things a little bit more challenging now. So let's say that they don't have the same mass. All right, so mass 1 is 1 kilogram, and let's say, yeah, it's traveling at 1 meter per second. Mass 2 is 2 kilograms, and it's traveling at 0.5 meters per second in the opposite direction. Okay? So, what is the total momentum of the system for this situation? And what's going to happen after they collide and stick together? What's going to happen when they collide? What's the total momentum? So what you're looking at here, this is like a snapshot before the collision. It's a moment in time, but everything's freeze framed. Mass 1 is 1 kilogram moving to the right at 1 meter per second. Mass 2 is 2 kilograms moving to the left at 1/2 meter per second. So what's the total momentum of the system composed of these 2 spheres? I know what this does. That's cool, it shows it for you. The momentum diagram shows you the total. Momentum 1, momentum 2. I think you know. So the total momentum is 0. Mass 1 has, good, Katie, momentum is 0. So they'll stop in place. Boom. Boom. They stop. So the total momentum after the collision is 0. The total momentum before the collision is 0, because you have +1 plus -1. Boom. The total momentum after the collision is 0. All right. What about now? So now I have a mass 1 that has a mass of half a kilogram moving to the right at 1 meter per second. So 0.5 times 1 is 0.5 kilograms meters per second. So mass 1 has 0.5 kilograms meters per second of momentum. Mass 2 moving to the left at half a meter per second, and its mass is 3 kilograms. So 3 times 0.5 is 1.5 kilograms meters per second. So if we call left negative and right positive, the total momentum of the system here is positive 0.5 plus negative 1.5. So you have positive momentum, negative momentum, the total is negative 1. So when they collide, okay, so you're still seeing the momentum of 1 and 2 separately, okay, momentum of mass 1 is 0.14, mass 2 is 0.86, but they're the same, they're basically combined now. But you see the sum, even if you look at them separately, the sum is 1 kilogram meter per second. So momentum is conserved. All right, let me turn on the kinetic energy here, and you'll see that kinetic energy is not conserved. Kinetic energy of the system here, 1/2 mv squared plus 1/2 mv squared is 0.63 joules. They collide, stick together. Now the total kinetic energy is 0.14 joules. So a lot of the energy has been lost. Energy is not conserved in this case, but momentum is conserved. Okay. Okay. So I'm avoiding doing actually writing equations on a page. Just trying this different approach out where we're just talking through this conceptually. But the problem-solving approach that you'll take for studying problems in this chapter is you'll have a system, and you'll use the this principle of conservation of momentum to write down an algebraic equation. All right, what is an equation? There's equal signs, there's a left-hand side and a right-hand side. Okay, so you're going to write down this algebraic equation. One side of the equation represents the situation before the collision. The other side represents the situation after the collision. Okay, so the one side is going to represent the total momentum of the system before the collision. The other side is the total momentum after the collision. The equal sign is the conservation part. They're equal. The total before equals the total after. And sounds simple, right? I mean, we'll start out looking at situations that are one-dimensional. So that means, some objects might have positive momentum, some objects might have negative momentums depending on your direction. But we could easily extend that to 2 dimensions. And then what we'll find is that momentum is conserved in both dimensions independent of the other. Kind of like how we split forces into x and y components, you can split momentums into x and y components, okay? But we'll see if we get to that far. But for the time being, in one dimension, you're setting up these equations where you are equating the situation momentum-wise before the collision with the situation after. All right. So I want to show you that so in the case of the inelastic collision, energy is not conserved. Energy drops. All right. Let me reset things here, and let's set up one of those situations where how did I have it? I had is hard to get it right at 1. Oh my gosh, there we go. Okay, so I'll set things up where mass 2 is twice as massive. You know, so mass and velocity play off one another in the case of momentum. They have twice the mass, but half the velocity. So they have the same magnitude momentums and pointing in opposite directions. 1 times 1 is 1, 0.5 times 2 is 1. So same momentums, opposite directions. And I have the inelastic case on here. So the total momentum is 0. And we can see that's true. After the collision, momentum is conserved, which means if they stick together, the total momentum is 0. I want to show you that that's, even if I change this to an elastic collision, this principle of energy conservation holds. Watch this. So they're not going to stick together, which means they don't come to rest after the collision. But what we should see is the total momentum is still 0. It is. So now, so essentially what we have here is, look at this, they change direction. So now mass 1 has a momentum of -1 kilogram meter per second. Mass 2 has a momentum of +1 kilograms meters per second. The total is still 0. Watch the momentum diagram down here. You see they flip direction? Okay. And you know, so here they both have, but let's change it so that it's not as perfect. Let's reset things. So here we have a situation. Try and make this 2. Not quite. Reset. Make them farther apart. Okay, so I'll set things up like this. So they have unequal masses and they have unequal momentums. So the total, so here you have mass 1 has momentum 1.5 kilograms meters per second to the right. Mass 2 has momentum 2 kilograms meters per second to the left. The total momentum of the system would be 1.5 plus negative 2.0. So the total momentum is negative 0.5 kilograms meters per second. All right, and I run things. Okay, so there's been an interaction. Individually, the momentums have changed. But if you look, now mass 1 has a momentum of 1.93 kilograms meters per second to the left. Mass 1, or mass 2, has a momentum of 1.44 kilograms meters per second to the right. So if we say this is a negative momentum and this is a positive momentum, the total is still negative 0.5 kilograms meters per second. Okay, let's reset things. All right, if it's an inelastic collision, the total is still negative 0.5 kilograms meters per second. So the situation, the dynamics of what happens is very different in the case of an inelastic versus an elastic collision, but this principle of momentum being conserved is true in both cases and everything in between. But now let's look at energy. Okay, let's reset things. So for the inelastic case, we'll look at kinetic energy. The system starts out with 1.75 joules of kinetic energy. After they collide and stick together, the energy is greatly diminished. So energy was not conserved. Momentum was conserved, but energy was not. Let's look at the elastic case, where the collision is perfectly elastic. Look at that. The energy was also conserved. Okay? Oh, sorry, you're not seeing this. Hold on. I keep forgetting to switch back and forth. I apologize. All right. Okay, so for the inelastic case, boom, they stick together, the kinetic energy drops. You start out with 1.7 joules. The energy drops to almost 0. For the elastic case, the kinetic energy doesn't change. Okay? Sorry, I keep forgetting to switch my sources. So what we see is, and that shouldn't be too surprising because elastic collisions are governed by elastic forces, springy forces. And what do we learn about springy forces? They're associated with energy being conserved, mechanical energy being conserved. So what will, in a few weeks when you guys do a computational investigation of collisions, what you'll see is in order to model collisions, what I actually do is I model the interaction between two objects as a spring force. And so when they're colliding, energy is being stored up as elastic potential energy, and then they bounce off one another, and that potential energy becomes kinetic again. So the mechanical energy is conserved in the case of an elastic collision. In the case of an inelastic collision, mechanical energy is not conserved. It changes. Why? Well, because that collision where things stick together involves things like deformation, things change shape. Whenever things change shape, there's internal friction in the material that makes up that thing, and that is energy being dissipated as heat, thermal energy. On the other hand, momentum is always conserved. In the absence of external influences, the momentum of the system internally is always conserved. Okay, so we'll call it a day there, and the next time on Wednesday, there's another problem set that's posted. It's due, I think, a week from Monday. I can't remember now. I think it's a week from Monday. You have quite a bit of time to work on it, and it deals with the concept of momentum and the concept of impulse, which we haven't defined yet. So next time on Friday, on Friday we'll do. I'm not sure recitation is. Let me think about it. Maybe we'll do a lecture on Friday instead of recitation. I'm not sure we've had enough introduction to this material to make recitation useful for us. I'll send out an email. All right, I'll let you guys know. But the next step is let's get quantitative, and we'll write down some equations, and then what I'll try to do for you is convince you that this principle of momentum conservation follows directly from Newton's third law. Okay, Newton's third law, which is this law that describes interactions, actions and reactions, is at the heart of momentum conservation. Okay, it's so I'll try to show you that and convince you that that's true. All right. Holly says, will the exam be graded by then? Because we could go over the exam on Friday. I can't. I don't know, Holly. I'm trying to get these things graded. I just have a lot on my plate right now. I'll do my best. Okay, I'll let you guys know tomorrow what's going to happen on Friday. All right. All right. Well, you guys have a great day, and I'll talk to you soon. All right. Bye bye.